American astronauts will explore the moon. When they do, their lives will depend on a mobile and self-sustaining life support system called the Apollo Extravehicular Mobility Unit. The system is one of several spacesuit designs being developed for the needs of manned exploration beyond Earth. To better understand the purpose of a lunar spacesuit, let's let our friend Andy Astronaut demonstrate the hazards lunar explorers will encounter. If Andy were to step out on the surface of the moon without a spacesuit, this is what would happen. In the near vacuum of space, the gases within his body would immediately expand. His blood would appear to boil from the rapid expansion of gases coming out of solution in his bloodstream. And he would soon feel the effects of another condition of space, lack of oxygen. After 20 seconds in a vacuum and without oxygen, Andy would be trading in his astronaut wings for a more permanent variety. But let's give Andy a break. At least now he has oxygen and a pressurized atmosphere. But it looks as though we forgot something. Since the moon, unlike the Earth, has no air layer to absorb the sun's rays, temperatures can reach 250 degrees Fahrenheit, well above the boiling point of water. There is also the problem of heat conduction. The soles of ordinary boots would provide scant insulation from the heat of the sunlit lunar surface. But that's not all. In addition, glare, infrared radiation, and ultraviolet rays from the sun could permanently damage Andy's eyes. The lunar night would hold an additional peril. The intense cold of space could quick freeze Andy to minus 271 degrees Fahrenheit, 300 degrees below the freezing point of water. Sorry, Andy, there's still another danger, high-velocity micrometeoroids. While the odds against a micrometeoroid hitting an astronaut are believed to be extremely low, any puncture would be decidedly uncomfortable. The Apollo Extravehicular Mobility Unit, or EMU, has been designed to protect astronauts from the hazards we have just seen. The unit is actually made up of several major components. These include a constant wear garment, a liquid-cooled undergarment, a pressure garment assembly including helmet, boots, and gloves, a portable life support system carried on the back, and a thermal micrometeoroid garment. The constant wear garment will be worn by Apollo flight crews during all non-extravehicular portions of lunar flight. Pockets at the waist hold biomedical instrumentation, which will help report the astronaut's physiological condition. Additional pockets on the chest and legs hold radiation measuring devices. Prior to commencing extravehicular activity, a crew member will remove his constant wear garment and don the liquid-cooled undergarment. The cooling garment will be worn under the pressure garment to carry off the astronaut's metabolic heat. Cooling is achieved by circulating cooled water through 265 feet of tiny plastic tubing, which is in contact with the skin. A dye has been injected into the cooling solution to illustrate the garment's tubing distribution and flow pattern. In a functional test of the cooling garment, a subject was dressed in Arctic survival clothing to minimize heat loss or gain. Purpose of the evaluation was to test the garment's flow temperature controls. The subject exercised in a 70-degree room temperature for 3 hours. He did not perceptibly perspire and remained comfortable the entire time. The pressure garment is constructed of an inner gas retention layer and an outer nylon covering designed to maintain the garment's shape against internal suit pressures. Specially designed joints provide for shoulder, elbow, wrist, thigh, knee, and ankle mobility. Operational use of the suit will be with a 100% oxygen atmosphere at 3.7 pounds per square inch pressure. This provides the amount of oxygen the astronaut would breathe if he were on the surface of the Earth. The helmet ensemble includes a soft cap which contains the headphones and microphones. The bubble helmet is placed over the head and secured to the pressure garment with a locking neck ring. The one-piece helmet construction provides unlimited visibility. Eye protection will be available in the form of an extravehicular visor assembly. The two visors control glare and the passage of ultraviolet and infrared radiation. They can be used singly or in combination. A small port on the side of the helmet provides for the injection of drinking water and squeeze foods. The port can also be used for supplying emergency oxygen. The helmet and visors are made of impact-resistant polycarbonate plastic. The slow-motion camera catches a 7-pound weight being dropped from a height of 4 feet onto a polycarbonate visor. The portable life support system weighs approximately 50 Earth pounds and will be used on all extravehicular missions. As shown in this schematic diagram, oxygen is fed into the pressure garment assembly where it picks up carbon dioxide, heat, and moisture. The expired gas then passes through a carbon dioxide absorbent, through a heat exchanger where the gas is cooled, and through a water separator which removes moisture from the gas stream. A fan maintains continuous gas circulation. The backpack also contains a water circulation system for removing the excess body heat picked up by the liquid-cooled undergarment. An immersed pump maintains a constant flow of liquid through the heat exchanger. The water separator is used to trap water vapor condensed as the gas stream passes through the heat exchanger. The water is collected in a reservoir where it builds up pressure against the bladder of a second water supply system. Water from the second system is forced through the heat exchanger where it is evaporated to the vacuum of space. The evaporative action provides the cooling of the gas and liquid loops. The backpack also contains a communications and telemetry package and a battery which supplies electrical power to the backpack equipment. An antenna is used to transmit bioinstrumentation data as well as two-way voice communication. In the event of a suit puncture or loss of the primary oxygen supply, lunar astronauts will have a secondary oxygen source in the form of this emergency oxygen supply system. A tug on the ball handle will release a 5-minute metered supply of oxygen. In this development model, the oxygen bottle is contained in a zippered pouch to facilitate attachment to the pressure garment. The feed hose would be inserted into the helmet before extravehicular activity is begun. When an astronaut steps into the extremes of heat and cold on the lunar surface, he will wear the thermal micrometeoroid garment as a means of minimizing temperature fluctuations within the EMU. The garment serves an additional purpose in protecting the astronaut against micrometeoroid impacts. The garment is chiefly constructed of alternating layers of Dacron and aluminized mylar sandwiched between a nylon cloth covering. Tests were conducted with the garment to evaluate its use with the EMU under simulated lunar surface conditions. An instrumented mannequin, heated to simulate the metabolic output of a working crewman, was placed in a developmental pressure suit fitted with a thermal micrometeoroid garment. The EMU assembly was placed in a vacuum chamber equipped to simulate the cold, solar heating, and infrared radiation of the lunar surface. The tests showed that the garment prevented any significant heat leak in or out of the EMU. Insulated sole sandals are being studied to protect the wearer against conductive heat loss or gain through the boot soles. The sandals would provide a larger tractive footprint in the relatively unknown lunar surface material. Exhaustive testing of the EMU components has included performance demonstrations under simulated lunar gravity. Lunar gravity, 1/6 that of Earth gravity, can be produced aboard aircraft flying parabolic trajectories. Such flights were used to determine helmet impact stresses during simulated lunar gravity. The subject, wearing an instrumented helmet, dove into a bed of rocks believed to approximate the size and type that will be found on the lunar surface. In an early test under lunar gravity conditions, a subject wearing a developmental pressure garment tried to right himself from a back-fallen position while wearing an early model of the portable life support system. The test revealed that an astronaut could not get to his feet while wearing the particular backpack design. The shape of the backpack container was restyled. The newer design proved satisfactory in allowing the subject to regain his footing. In early suit mobility studies, the apparent lack of ankle mobility in the inflated boot was noticed. Subsequent X-ray studies by NASA's Manned Spacecraft Center, Houston, Texas, and the Baylor University College of Medicine provided a unique insight into human joint mobility range and the restrictions imposed on mobility by spacesuit fixtures. Data resulting from the study aided the redesign of suit features to produce the desired mobility range. A major portion of an astronaut's duties on the moon will consist of setting up experiments and taking scientific measurements. The equipment for these experiments will be packed in special boxes carried in the lunar module's descent stage. To determine the astronaut's ability to remove and handle the scientific packages under 1/6 gravity conditions, parabolic flights were again made in the KC-135. 6 test packages were used, ranging in weight from 45 to 180 Earth pounds. The subject experienced no difficulty in handling the heaviest load. Suit mobility and task studies were conducted in terrain of volcanic origin near Bend, Oregon. Such terrain is believed to approximate lunar topography and surface composition. The tests showed that a spacesuited astronaut in an Earth gravity condition could perform the geological tasks necessary for scientific lunar exploration. To simulate prolonged reduced gravity conditions, a 6 degree of freedom simulator is being used in conjunction with a simulated lunar landscape constructed at the Manned Spacecraft Center. The counterweighted device is transportable and interfaces with spacecraft mock-ups. However, the device's large mass requires extra effort to initiate and control its movements. While it lacks portability, mass is not a problem with this reduced gravity simulator built by NASA's Langley Research Center, Hampton, Virginia. The subject is fitted with a harness which is attached by wires to an overhead trolley. The runway is tilted to produce the lunar gravity gradient. extravehicular mobility unit is being developed for preliminary lunar surface investigations. Other systems, such as this hard suit of metal and fiberglass, are being evaluated for use in later lunar scientific exploration and possible deep space applications. The hard suit has constant volume joints designed to hold the suit's 5 pounds per square inch operating pressure. Whatever form they take, the mobile life support systems that man carries with him into space will benefit from the experience gained in the development of the Apollo Extravehicular Mobility Unit. The EMU is one of many technical accomplishments accruing in the pursuit of our national goal, United States leadership in space.